Hi, welcome to the demo session of week 2 of the Haskell course on NPTEL. So, in this session, we will look at some of the functions we have seen in the previous lectures, mainly concerning with recursion on integers and recursion on lists. But before we do that, there was one aspect that I had mentioned in the first week's lecture, which I would like to go through. So far, we have been writing programs in some Haskell file and we have been loading it into GHCI and we have been running it. But I mentioned that there is also a way to run Haskell programs standalone. So, the simplest way is to write a program. I have a hello.hs here. As I mentioned, standalone programs must have a main function. You might not understand much of this program right now. It doesn't matter. In 4 or 5 weeks, we will actually go through input output in detail. But for now, all you need to know is that main should have type IO followed by something. Typically, it will be IO followed by this thing with an open parenthesis and a closed parenthesis. For now, don't worry about what it means. Just think of it as some standard template. You always write main : IO empty parenthesis, and then here is a very simple program. You can of course do much more, but in this program all I am doing is writing hello world. Okay, this is a hello world program. One of the things that this uses is what is called put string line. Okay, you want to put a string on a line on the display, on the output device, whatever the output device is. You write like this. Right now you don't need to worry about what the function is actually doing, but all you need to know is how to write such programs and run them. The way to run them is to go to the command line and say GHC rather than GHCI and give the name of the program. Test.hs is the name of the file. You have to give the name of the file. No, hello.hs is the name of the file. That generates a bunch of files. Among those, you notice that if I now say ls hello, you already see that there is a hello.exe, which is an executable file. Hello.hi, hello.o, these are some intermediate forms which you don't need to worry about. On Windows machines, you will have something called hello.exe. On a Mac or Linux machine, you will have something .hello. You will have something called hello, hello. That's it, without any suffix or prefix. Importantly, though, if you look at ls hello star. Okay, so on Windows it doesn't show this, but on a Mac or Linux, if you see, you will see that this mode, it will have some different permissions, and it will tell you that it's an executable function. Here it says .exe. On a Mac or Linux, there will be some modes which are written in terms of RWX, and normal files will only be RW, whereas this will be RWX. Okay. So that is the point. Now, once you have a thing like this on Windows, you can on the terminal on Windows, you can execute this by saying ./hello.exe. Maybe one has to link it. Yes. So yes. So it takes a while, but it comes back and gives you this. Maybe the second time it will come quicker. Yeah, so I think it was linking some libraries the first time. You can change it, of course. You can put multiple lines of output, but if you want to do that, you have to put it in something called a do block. Okay, you can do this, save this file, and you can go to the terminal, and you can once again compile this, and you can once again run it. Now it will print 2 lines. For some reason on Windows it takes a while to link, on the Mac and Linux it is much quicker. Yeah, so there was a mistake I did. I should have put a space here. So let's recompile. On your own machines, if you are running a Windows or Linux, it should be easier. It should run quicker. If you are running a Mac or a Linux, one has to figure out why this delay is happening on Windows, but it's okay, let's not worry about it now. Okay, so here is how you write standalone programs, compile and run them. But for the moment, let's not worry about this. We'll mostly be working with GHCI. Okay, so let's close this hello.hs and let's start GHCI. Here you see that I have already written many programs that we talked about earlier. Factorial here, I have given it as this. If n is greater than 0, then it's n times factorial n minus 1. If n is equal to 0, it's 1. Otherwise, it's a negative input. So you just say error. And here is the program for my GCD, where we say that my GCD of AB, if A is less than 0 or B is less than 0, it's my GCD of absolute value of A and absolute value of B. B is 0, then you return A as the value of this function. Otherwise, the value of my GCD AB is just the same as the value of my GCD B, A mod B. Okay, so you can run this on various inputs. So let's load this. I have called this program week 2 program 1. It's been loaded. So now I can say my GCD. I can try various numbers, 120, 24, that's 24, 120, 25, let's try, and I should get 5. I'm getting 5. Maybe I'll try my GCD of 25, 120, I'll again get 5. Yeah, so I can do this. Suppose you want more information, suppose you just want to see how the value is computed. Now that we have learnt lists, one can actually do this thing, that you don't just return an integer, but you return a, let's say I call it my GCD trace, which traces all the recursive calls. I'll call it GCD trace. And it's more convenient to use pairs here. I'll use pairs. Okay, so this is a challenging program. Let's see. What do I want to do? What I want to do is the following. If I have, by the way, how do you comment out lines in a Haskell file? You do it by saying hyphen hyphen on a line, or you use brace hyphen and then that's a block, and you end it with hyphen brace. So that's a multi-line comment. So let's look at this. So GCD trace of, let's say something like 120, 25 should produce a list, and the list is it produces the sequence of all the recursive calls that have been made. So 125, 20, 120, 25 will make a recursive call to 25, 15. 25, 20, which will make a recursive call to 25, which will make a recursive call to 50, and you are supposed to stop at this point. Okay, so let's write this program. This program is not actually analyzing any list, it's just building a list. Okay, so and the list is just there to tell you how the computation evolves. So GCD trace of AB equals, we will just follow the same guarded notation. If A is less than 0 or B is less than 0, then it is just GCD trace of it is AB followed by GCD trace of absolute value of A, comma absolute value of B. If B is equal to 0, then it is just AB. You have to stop at this point. Otherwise, it is AB followed by GCD trace of B and A mod B. This will give you a, so in the case when B is equal to 0, you have to return the singleton list AB, not just AB, not just the pair, but a singleton list containing the pair, right. So this is how you build a list which tells you how this program evolves. For various other integer functions, you can also try to build similar kinds of traces to see how, to get a better understanding of how the computation evolves. Let's save this. Let's reload the function. Okay, it compiles. Let's look at GCD trace of 120, 24. Yeah, so you see that you get a list consisting of two pairs, 120, 24, 24, 0, and you stop there. GCD trace of minus 120 to 24, let's try. Okay, so I wanted to try minus 120, 24. Yeah, the first call is minus 120, 24. The second call is 120, 24 because it takes the absolute value, and then it's 24, 0. Right, so now you can actually have fun trying out various values for this. GCD trace of 121, 625, let's say, yeah, something like this. So 121, 625, the first time it calls, it flips because it says A, B, B and A mod B, so it flips, but after that it is always the case that A is greater than or equal to B. So now it's 121, 20, 21 and 10. So 121 and 625 are relatively prime, so you will get 1 as the GCD. And you can try various values like this, 127, 625, let's try. So you have that, and so on and so forth. Okay. So yeah, so this is about GCD. Here is the function which we talked about. There are two versions here, one which tries to check. So this is a function which checks if the given number is a power of 5. Is POF n, if n is less than or equal to 0, it's false. If n is 1, then it's true. Otherwise, you check whether n mod 5 equal to 0, and only if that check passes, you check whether n divided by 5 is also a power of 5. So if we can test this, so is POF 625 should return true. Is POF 5 to the power 1000 should also return true. Is P of 5 to the power 1000 minus 1 should return false. Or something else like is POF of 4 times 5 to the 20, that should also return false. Okay, so fine. So this is about power of 5, and here you see that this is the alternative version where we are checking whether here we define a function. Typically when you want to define a local function whose name you don't care about much and which is not visible outside this local scope, you just call it go. Okay, that's a very convenient Haskell convention that you call these functions go. And is POF of n is go 1, where here what we are doing is we are starting from 1 and repeatedly multiplying by 5 and see whether we reach n. If p at some point of time reaches n, then you say true. If p overshoots n, then you say false. As long as p is less than n, you keep multiplying p by 5 and checking whether you reach n or not. Okay, and then here are some of these functions that we saw already. Largest div is yeah, so we directly did the largest div. We also did the so you have the largest div function. Here is the int reverse function, which we have written by reversing the integer into an accumulator. If n is less than 0, then you want to signal an error. Otherwise, you want to reverse to the accumulator 0 the number n. And reversing n to the accumulator a is nothing but if n is equal to 0, then you return then the value is just the accumulator. Else you let dm be n div mod 10, and then you first modify the value of accumulator by you take a new accumulator really by doing 10 times a plus m. What this does is to attach m to the rightmost digit of the accumulator, attach m as the rightmost digit to the right of the accumulator, and then you reverse d into the new accumulator. Okay, so this is what you want to do. And once again, if you want to have a clear idea of how this thing proceeds, you could do a trace for this. Let's actually write a program that traces this. RTA I'll call for reverse to accumulator, and I'll assume for simplicity that we are given to a pair of integers, and I'll produce a list of pairs of integers which will tell you the various recursive calls. And this pattern is the RTA trace, I should call it. And this pattern is the same as the pattern for the GCD trace that we saw earlier. RTA trace of a comma n, a is the accumulator and n is the number. If n equals 0, then there is no recursive call to be made. It is just a singleton list a n. Else, or maybe it's easier here to do guarded notation. In case the guard n equals 0 passes, then the value is actually the list a n. Otherwise, it is a n followed by RTA trace of 10 times A plus M comma D, where dm equals n div mod 2, n div mod 10. Let's see how this works. Let's reload this file. It compiles, thankfully. RTA trace. Let's say 1, 2, 3, 4, 5. The accumulator is 0, let's say. And then what we want to reverse is 1, 3, 5, 6, 7, 9, 8, 3, 2, 1, 4, some such thing. Let's see what happens. See, let's first start with a simpler example just to illustrate what is happening. 1, 3, 2, 5, 7, let's say. Yeah, the first call is to 0, 1, 3, 2, 5, 7. You see in the next step it becomes 7, 1, 3, 2, 5. Then it becomes 75, 1, 3, 2 because the 5 at the end of 1, 3, 2, 5 is added to the end of 7. It becomes 75. Now, the 2 at the end of 1, 3, 2 is added to the end of 75, to the right of 75, so it becomes 752, 13. Now, the 3 at the end of 13 is added to the right of 752, it becomes 752, 1. Then the 1 at the end of that is added to this, and that the 1 div mod 10 will actually, the mod will be, the div value will be 0. So, you hit a 0, so you will stop at that point. And you can see that, you can also check that if I have something like RTA trace of 0, 10,000, let's say, you see that the 0 keeps getting added to the right of 0, but then 0, 0 is not a number, it's only 0. So, eventually you will reach the point where you receive 0, 1 and then 1, 0 it will become, which is clear, right? Because the reverse of 10,000 is 0, 0, 0, 0, 1, but 0, 0, 0 is discounted and you just call it the number 1. Okay, so you can use lists to even gain more information about integer functions. You can do these traces. Here is a function I have written for power, and then I have written it for faster power. Okay, this is more or less the same thing that we wrote earlier. Here is the Fibonacci numbers. Fibonacci numbers is a little tricky because there are two recursive calls. Fib_n calls fib_n-1 and fib_n-2. So rather I use a small trick, which is that I always produce two numbers. So fib prime 0 will produce fib of 0 and fib of 1. Fib prime of 1 will produce fib of 1 and fib of 2. Similarly, fib prime of n will produce fib of n and fib of n plus 1. So this is easy because I have two values. So if I have fib prime of n minus 1 already, let's call it the pair x comma y, I can compute fib prime of n by just moving y to the first component and then adding the two components and putting it into the second part. Okay, so instead of xy you will have y comma x plus y. Okay, and finally if you want the Fibonacci number, you will just say FST is a function that extracts the first part of a pair. So I can go here and I do FST of 2, 5, I will get 2. If I do SND of 2, 5, I will get 5. Okay, so these are about integer functions. Now let's come to the list functions. We saw many of these, so let's try to understand these. So here is the add one function, and notice that I have used the null etc. style, but of course if I try to actually use head and tail, let's see what happens. On my machine it refuses to compile. Maybe on this Windows machine it might compile. Let's see what happens. Let me comment out this. And let's come here and let me comment out these by control slash. Okay, let me add some add one L. Let's try to compile this function, this program. Try to reload. See, you get a, okay, it's not an error, it's a warning, so it's fine. So there is a difference between an error and a warning. Warning will still go through, the program will compile and you can actually run the program, but it's an irritating warning. So therefore, if you want to avoid this warning, you should go ahead and do it like this. You can use patterns like this, or much better, you can directly define this thing using pattern matching, like I showed in the slides. Okay, I have uncommented these lines. Let me save this again and reload. I have uncommented the wrong line, so let me fix it. Okay, now everything compiles and you can run these programs as usual. Yeah, so here is a version of length mylen, I am calling it, using pattern matching. Mylen of empty list is 0, mylen of anything followed by x's is 1 plus mylen of x's. Notice the underscore here, which says that I don't care what the actual value of the first element is. Here is a, okay, so here is a nice feature. Recall that I told you that you can use operators as functions by putting them inside parentheses. What are operators? Operators are anything that does not start with these English letters. Okay, for the moment just treat it like that. So hash is clearly not a letter. So hash is an operator, but I want to define it as a function, so I can put, I am saying the function is hash within parentheses, that is the name of my function, and this, what it does is to add one integer at the end of a list of integers, and when I define, I can just use it infix. I can, even on the left hand side, I can use it as infix. This is when you define operators, you might say, for instance, that m plus 0 equals m plus successor of n is nothing but successor of m plus n. You can do that. So you're defining this operator. You're saying empty list hash x is just singleton list x. Y colon y is hash x is nothing but y colon y is hash x. Let's try this. Let's try 2, 3, 4 hash 1, let's say. Yeah, we get 2, 3, 4, 1, right? Good. So once you have hash, you can actually do append. There are two appends. Remember that we have two appends, one which does induction on the recursion on the second list, one which does recursion on the first list. This version says append L1 of x colon x's is nothing but append 1 of L1 colon x x's, whereas this says append 2 of x colon x's followed by L2 is x colon append 2 of x's L2. Okay, this is the standard version, and this is the function where I wrote value at position. Okay, we can actually check various cases for this. We can check value at position 20, let us say, for the list 1, 2, 3, 4. I should get an error saying index too large. See, I get an error saying index too large, exception index too large is what it says. Whereas if I say value at position 2 of 1, 2, 3, 4, I must get the value 3 because the indices start from 0. So at index 0 you have the value 1, at index 1 you have the value 2, and at index 2 you have the value 3. So you should get 3, right. If I say value at position of minus 22 of 1, 2, 3, 4, you should say negative index not allowed. Even if you try to extract the thing at some negative index for the empty list, it should say negative index not allowed. If you say value at position of 0 empty list, it should still say index too large, right. So all these cases have been handled with this value of position, but this is the same as the bang bang operator. So you can see that if I do 1, 2, 3, 4, bang bang 2, I'll get 3, bang bang 20, I'll get some error saying index too large, okay. And yes, finally we have this reverse function. So one version of reverse is to just reverse the tail and then put the first element at the very end. Another version of reverse is to use an accumulator, reverse into the accumulator ACC, rev into arc of empty list is ACC, rev into arc of x colon xs is rev into x colon arc of xs. Finally you have fast reverse because it is much faster than my reverse, is just reverse into the empty list as the accumulator, okay. And notice that I am ignoring the, ideally I should have written fast reverse, fast rev of L equals rev into empty list L, but recall that we already noticed that if I have to say XOR B1 B2 equals not equal to applied on B1 B2, instead we could have just said XOR prime is just equal to not equal to. Yeah, so similarly you can omit any number of arguments like this, provided that all you are doing is constructing some expression and applying it on L, right. So fast reverse you want to apply it on L, what is it? You are constructing some expression using reverse into and then you are applying it into L. So rather than saying fast rev of L equals some expression applied on L, you can just say fast reverse is equal to that expression, okay. So that's this. So let's actually check the difference in time between fast reverse and my reverse. Let's see what happens. Sometimes when Haskell complains about some error involving type, you actually give an explicit type and it will work. Yeah, it works. So now let's try to reverse a fairly long list. Okay, so here I'll let you in on a secret. How do you write fairly long lists? I can write 1, 2, 3, 4, etc., but I can't write 1 to 1000. There is a nice shortcut in Haskell. I just say 1 dot dot 1000. That means it's all elements from 1 to 1000. Let's do reverse of 1 to 1000. It's quick. Let's do my rev of 1 to 1000. You can see that there was a mild stutter. Let's try fast rev of. If I increase it to 10,000, you will see that the difference is more noticeable. Okay. It started to print immediately. Let's see what happens to my rev. You can see that it's much slower, even though it picks up speed as it goes along. This was much quicker. One can notice the definite slowing down, but if we increase the length, it will become much more pronounced. See, this really takes a long time. So let's abort, because we can't sit and stare at this all day long. You abort a program by clicking Control C. Okay, but let's try FastRev on this. See, it's much quicker, it zips past. And actually for this we can even afford to wait for a little bit to see when it finishes. See, it's finished before I could complete my sentence, whereas the earlier myrovers took a while. So this already tells you, so the aim of this course is not just to learn programming in Haskell, but also to appreciate various trade-offs in programming, and also one of the main things you want to learn is to measure how well a program performs. And you can see that this really starkly tells you the difference between n squared and n, right? So the point is that as you for smaller values of n, if I just tried for even 1 to 10,000, I didn't see much of a difference. 1 to 1000, I will certainly not see any difference between FastRev and myrev. It won't be noticeable to the naked eye. See, but if once I increase it to 50,000, then this really struggles, right? And whatever it's still at 42,000 or 42,000 or whatever. Yeah, we really can't afford to see it. It was only at 43,000 when I interrupted it. Whereas if I try FastRev of 50,000, it was much quicker, really. And it really finished. We are already in the 30,000s, and yeah, this will end soon now. Yeah, right. So I hope you appreciate the difference between n squared and n, which is the amount of work required between myrev and FastRev. Okay, so I shall close this demo session now. You will be able to explore more list functions in the exercises. In the next week lectures, we will go deeper into list functions. Thank you.